Today, we're going somewhere outsiders are strictly forbidden. Texas, Brownsville, international shipbreaking. Right behind me, the USS Kitty Hawk is living out its final days. A legendary aircraft carrier, a true floating fortress. Just imagine, what struck fear across the oceans for decades is now being torn apart by giant shears. Today, I'm taking you behind the scenes of this metal inferno, where they're cutting up history. You'll hear the screech of steel that'll make your ears ring. Let's go. This is gonna be huge. When a giant aircraft carrier, like the legendary USS Kitty Hawk, drops anchor for the last time off the coast of Texas in Brownsville, it's not just the end of a ship's service, it's the end of an entire era. But what happens to the very backbone of that carrier? Its anchor chain? Welcome to the Graveyard of Titans, a place where metal gods die to be born again. The first thing that knocks you off your feet in Brownsville isn't the heat. It's the visual weight of scale. When you see an aircraft carrier's anchor chain on deck, it looks big. When it's lying on shore, dumped in a massive pile, it looks like a scene from an apocalypse movie. The anchor chain of a Kitty Hawk class carrier weighs as much as a full freight train. Each individual link is a steel block weighing over 330 pounds. Picture this. One ring of this chain weighs more than 2 grown men. And there are thousands of these links. When they lower this chain to the ground, it forms mountains. The height of this pile of iron easily reaches the level of a 3-story building. Standing next to it, you feel like an insect at the feet of a metal colossus. This chain held an 80,000-ton behemoth in the middle of a stormy ocean for decades, and now it looks like a motionless serpent, its skin covered in layers of rust, salt, and history. To destroy such a chain, they use giant hydraulic shears, known as shears. These are steel jaws of incredible power, mounted on heavy excavators. The process looks mesmerizing and terrifying at the same time. The operator brings the shears up to a link in the chain, steel as thick as an adult's leg. You hear only a brief crescendo of hydraulic rumble, and then a sharp, dry sound, like a gunshot. Hydraulics bite through a giant link as easily as you snap a toothpick. No sparks, no smoke, no resistance, just pure mechanical advantage. Steel crumbles into fragments under hundreds of tons of pressure. It's the moment you realize nothing lasts forever. Even the toughest hardened steel, built for war and ocean survival, yields to the engineering genius of modern recycling. When we talk about anchor chains and hull steel from giants like the USS Kitty Hawk, we're talking top-tier metal that outperforms most of what's mass-produced today. This is high-grade steel, tempered by decades of service in the brutal ocean environment, and its journey from a Texas processing plant to the body of a brand-new Tesla. First off, you need to understand the value of the metal itself. The steel used in aircraft carriers was made to survive extreme conditions. Massive pressure, constant corrosion from salt water, colossal vibrations, and temperature swings. This isn't the metal they make tin cans from. This is low-alloy, high-strength steel that produces minimal waste during recycling and practically doesn't lose its physical properties after remelting. Economically speaking, recycling a carrier in Brownsville is like mining pure gold in the world of ferrous metallurgy. Every ton of this metal is far more valuable than ordinary scrap because it requires less purification and fewer additives when creating new alloys. The transformation process begins with pieces of chains and hull plating cut by hydraulic shears being loaded into giant buckets and sent to steel mills. The main character at this stage? The electric arc furnace. Unlike outdated blast furnaces that need ore and coal, electric arc furnaces run primarily on scrap. It's the perfect machine for rebooting metal. When multi-ton chunks of aircraft carrier chain hit this hellish circle, an arc flashes between the graphite electrodes at over 5,000 degrees Fahrenheit. In that blinding light, the ship's past literally evaporates. Rust, paint, and salt float to the surface as slag, while pure, molten top-grade steel settles at the bottom. This is the moment the economic future is born. Thanks to the high purity of the starting material, steelmakers can tune this melt for specific orders with minimal cost. If the market needs ultra-strong steel for the auto industry, they add precise doses of alloying elements to the furnace. And this is where Tesla comes in. Modern automotive manufacturing, especially electric vehicle production, demands metal with a perfect balance of weight and strength. Steel that once held a crew of thousands aboard an aircraft carrier through violent storms now becomes safety pillars, suspension components, or structural frames for electric cars. It's a remarkable paradox. A former symbol of military might that burned thousands of gallons of fuel oil per hour is reborn as environmentally clean transportation running on electricity. But automobiles are only part of the story. A huge portion of high-grade steel from Texas shipyards flows into the construction sector. Modern skyscrapers in Dubai, New York, or Shanghai need rebar and beams capable of withstanding colossal static and wind loads. Using recycled aircraft carrier steel in construction isn't just about cost savings, it's about prestige and environmental responsibility. Today's architects and developers fight tooth and nail for LEED certifications, awarded for using recycled materials. So the steel backbone of the old USS Kitty Hawk literally becomes the backbone of a new financial center or luxury residential complex. The economic logic of this process is backed by a global push toward decarbonization. Producing steel from scrap in electric arc furnaces emits 70 to 80% less carbon dioxide than traditional production from ore. For big corporations like Tesla or construction giants, this is critical for their sustainability reports. In other words, when they buy a chopped-up aircraft carrier, they're not just buying metal, they're buying green points for their reputation. Ultimately, this transformation carries deep philosophical and financial undertones. The carrier's steel was purchased with taxpayer money decades ago as an investment in national security. Now, through the recycling process, that investment returns to the civilian economy. And have you subscribed to the fascinating space of my channel yet? If not, now's the perfect time. Once electric arc furnaces melt down the carrier's steel, it emerges as glowing ingots or continuous strips, ready for a new life. Thanks to its exceptional purity, this metal becomes the foundation for critically important components. From ultra-strong truck axles bearing tons of cargo to surgical instruments or intricate parts of aircraft engines. Some of the metal gets transformed into massive I-beams that'll become the skeletons of new stadiums or bridges, capable of standing for centuries. There's a real irony here. Steel that was once created to carry planes and cannons is now being reborn as tools of creation. From the blade of a kitchen knife in your home to high-tech medical equipment that saves lives. When you look at those giant hydraulic shears in Brownsville, you're not just seeing destruction. You're seeing the first stage of creating something new. Every yard of chain that gets cut is a contribution to the foundation of a future skyscraper, or the body of the next technological breakthrough on wheels. This is the true graveyard of titans, where every death is just the beginning of a new, longer, and more useful life. You stand on the edge of Hudson Yards and look down, you won't see ground. You'll see steel, concrete, and 30 active rail lines with hundreds of Long Island Railroad trains barreling through every single day. This is West Side Yard, a rail depot that for decades was a black hole right in the heart of the world's most expensive island. There was nowhere to build because there was nowhere to sink a foundation. But in New York, they say, if there's no land, we'll make it. That's how the most expensive private development project in US history was born. $25 billion. This is Hudson Yards, a city hanging on steel threads above an operating railroad. Let's go check it out. Picture this. You need to build an entire neighborhood. Office towers, parks, shopping centers, apartment buildings. But you can't stop the trains running underneath. You can't just pour concrete everywhere. You have to build a roof over the depot that can hold the weight of an entire district. To pull this off, engineers had to create a platform. But this isn't just a slab. It's a titanic engineering masterpiece held up by 300 concrete columns, driven right between the train tracks. There was zero room for error. A deviation of a few inches would mean a column landing right on the rails. But the columns are just the support structure. The real heroes of this story? Steel trusses. When we say beam, we usually picture something a couple of workers can lift. Forget that. For Hudson Yards, they fabricated the largest steel trusses ever seen in construction. One of these beams weighs 100 tons. That's like 3 fully loaded semis, or 20 adult elephants, concentrated in a single piece of metal. These trusses were manufactured at specialized plants and delivered to Manhattan at night, when the city sleeps. And it's exactly this plant we're heading to today. When the giant crane starts lifting the 100-ton truss, you hear the steel cables pulling tight. It's the sound of high tension. The air around you seems to thicken. The crane operator works with the precision of a surgeon. The beam has to be lowered onto the caissons, so the gaps don't exceed millimeters. 100 tons of steel glides smoothly over the train sitting below. One wrong move, and billions of dollars, plus the safety of New York's entire transportation system, go down the drain. When the beam finally settles into place, the welders and riggers get to work. You see sparks flying from 10 stories up. Each beam is secured with bolts the size of a human head. But here's the secret. Since the railway below keeps running, the platform is constantly hit by vibrations from trains. If it were rigid, it would just crack. So Hudson Yards breathes. Built into the structure are giant shock absorbers and hinges that let the metal skeleton shift a few inches, soaking up the energy from the railway chaos underneath. There's heat here too, but it's the heat of glowing metal and welding torches. Even in winter, when icy wind blows off the Hudson, it's warm near these beams. They hold the energy of construction. Once all the beams are in place, they pour a concrete slab on top. That's how you create new ground. On this steel base, they planted over 200 trees and thousands of plants. But there's a catch. Tree roots can't grow deep, because down there, beams and trains. Engineers created smart soil. Under the park runs a complex cooling system. Why? Because the trains below put out so much heat that tree roots could literally cook. The Hudson Yards platform is a giant air conditioner for a forest hanging over an abyss. Sounds like science fiction, but the trees in Hudson Yards Park live in a refrigerator. Because dozens of diesel locomotives operate below, the platform heats up intensely. To keep the tree roots from cooking, a network of tubes circulating liquid is embedded in the concrete slab, drawing away excess heat. The soil itself isn't just dirt. It's a complex mix of sand, porous minerals, and fertilizer that weighs 30% less than regular soil, so the beams don't buckle under the weight of the forest. Today, Hudson Yards is gleaming glass towers, luxury boutiques, and the famous vessel installation. Tourists snap selfies, never suspecting that right beneath their feet, hidden under layers of concrete and granite, a steel army holds the line. You'll never see dumpsters or stinking garbage trucks on the streets of this neighborhood. Underground, there's a system of vacuum tubes. You toss a bag into the chute, and at over 40 miles per hour, it gets sucked by a powerful airflow straight to the central waste collection terminal. This frees the streets from traffic jams and rats. Those same 100-ton trusses are the atlases of our time. They don't complain, they don't get tired. They just carry $25 billion and architects' dreams on their shoulders. I've already told you so much about the benefits of these beams, and now's the perfect time to see how they're made. So you're coming on this journey with me right now. Manufacturing beams for Hudson Yards is a challenge taken on by only a handful of plants in the US, including Banker Steel in Virginia. Regular construction steel won't cut it here. When you've got a multi-billion-dollar skyscraper standing on your shoulders, you can't afford a single micro crack. In a massive cauldron, liquid iron boils at temperatures exceeding 2,900 degrees Fahrenheit. Precise doses of vanadium are added, along with what seems like a pinch of other elements, to make the metal simultaneously hard as diamond and flexible enough to withstand the vibrations of trains and wind loads from the ocean. Steel arrives at the plant as massive slabs. Some are 6 or even 8 inches thick. These are monolithic steel plates. First step, cutting. Regular saws don't work here. Giant computer-controlled plasma or laser cutting tables are used instead. You see a blinding blue flame slice through the steel slab as easily as a hot knife cuts through butter. The screech of metal is so loud, the windows vibrate for blocks around. Each piece of the future beam is cut with surgical precision. Once the parts are ready, they're assembled into a single structure. A truss is a complex geometric network of top and bottom chords and diagonal braces. The assembly shop is where bridge cranes rule. Parts weighing 10 to 15 tons get hoisted and positioned on special jigs. Welders use magnetic clamps and hydraulic presses to bring the plate edges together. Each joint gets locked with temporary welds, tack welds. At this stage, the beam already looks imposing, but it's still fragile. Welding is the longest phase. For plates this thick, they use submerged arc welding. A massive manipulator crawls along the seam, burying it under special powder while an electric arc burns inside. This prevents metal spatter and keeps oxygen out of the weld. The weld seam on a 100-ton beam can run several inches thick and consist of 30 or 40 layers of metal. That takes days, but subscribing to this channel takes less than a second. Have you made that one click yet? The temperature in the welding zone is so high that the metal glows cherry red. You can smell that dry, stinging scent of ozone and molten flux. When the beam is ready, it goes through a medical examination. Not a single weld is taken on faith. Non-destructive testing specialists scan every inch of welding with ultrasonic sensors. They're searching for microscopic air bubbles or slag inclusions. If they find any, the weld gets cut out and rewelded from scratch. Hudson Yard Safety accepts no compromise. The final step, corrosion protection. The beam is shot blasted to a shine, then coated with multiple layers of specialized epoxy enamel. The color is usually gray or red. Then comes the toughest part, delivery. The beam won't fit on a regular flatbed. It's hauled on special multi-axle trailers where each wheel can pivot independently. The route to New York is calculated months in advance. Will the bridge hold? Will the trailer clear the overpass? Getting a single 100-ton beam to the construction site cost $50,000 to $70,000 in transportation alone. The route from Virginia to New York took several days. Every bridge along the way was checked to see if it could handle such a concentrated load. When the trailer rolled onto Manhattan, police shut down entire blocks because the turning radius of that beast required the full width of the avenue. Right now, you're holding the result of an African tragedy in your hands. Inside your smartphone, laptop, gaming console are tiny components made from a metal mined in the jungles of Congo, where actual wars are fought over it. This is coltan, a dull black rock that looks like an ordinary river stone but costs thousands of dollars per pound, and without which no modern electronics would work. Millions of people have been killed for this rock. Its extraction finances armed groups, destroys guerrilla reserves, and turns people into slaves. But without it, your phone wouldn't exist. Let's peer into the dark world of the most controversial mineral of the digital age, where every like and every post carries the price of a human life. First, the terminology. Coltan isn't an official mineral name. It's short for columbite tantalite. It's an ore containing two metals, niobium, which used to be called columbium, and tantalum. It's tantalum that makes coltan so valuable. It's a silvery gray metal with a unique combination of properties. It doesn't corrode at all, withstands extreme temperatures, has high capacitance, and barely conducts electricity because of a thin oxide film on its surface. That last property revolutionized electronics. Tantalum is used to make capacitors, components that store and discharge electrical charge. Tantalum capacitors are microscopic, the size of a grain of sand, but they have enormous capacitance. They're stable, reliable, work for years without degrading. Every smartphone contains 40 to 50 tantalum capacitors. a laptop, up to 100, gaming consoles, cameras, even electric toothbrushes. Tantalum's everywhere. Coltan looks like black or dark gray rock with a metallic shine. Heavy, density around 8 grams per cubic centimeter, almost like lead. If you pick up coltan, you feel it's unusually heavy for its size. It occurs as coarse crystals or grainy masses in granite formations. Nothing special to look at, just a rock. But you can get anywhere from $100 to $400 per kilogram, depending on tantalum concentration. The main problem with coltan is geography. About 60% of the world's reserves are in one place. The eastern provinces of the Democratic Republic of Congo, especially Kivu and Ituri. This is one of the most dangerous regions on the planet. For decades, there's been a civil war involving dozens of armed groups that control the mines and use the profits to buy weapons. The story of the coltan rush began at the turn of the millennium. In the early 2000s, demand for tantalum exploded due to a boom in mobile phone and gaming console production. Sony released the PlayStation 2, Nokia and other manufacturers were churning out millions of phones. The price of coltan skyrocketed from $30 to nearly $400 per kilogram. A real gold rush started in Congo, only black. Tens of thousands of people dropped everything and headed into the jungle to dig for coltan. Armed groups seized control of the deposits. Murders, rapes, forced labor began. Kahuzi-Biega National Park, home to mountain gorillas, was overrun by miners. Animals were killed for meat or simply because they got in the way. The gorilla population plummeted by 90% in just a few years. The UN published a report confirming that coltan sales were financing a conflict that had claimed millions of lives. The bloodiest war since World War II. Armed groups controlled the mines, forcing local populations to work for free or for pennies, smuggling coltan through Rwanda and Uganda, selling it to middlemen who shipped it to China and Europe for processing. Coltan extraction in Congo is mostly artisanal, meaning small scale, no machinery. Miners work in rivers and streams, washing ore in pans like gold prospectors. Coltan's heavier than regular sand and pebbles, so it settles at the bottom of the pan. Or they dig pits in the forest, sometimes 30 feet deep, with no reinforcement. Cave-ins kill people regularly, but nobody keeps track. The working conditions are horrific. People stand waist-deep in murky water all day long, washing tons of rock for just a few pounds of coltan. They make $1 to $5 a day. More than farming, but still poverty. No safety, no rights. Kids work right alongside adults. Women are forced into labor, or worse. Coltan gets collected, dried, and sold to local traders. They haul it to regional centers where Chinese and other foreign companies have warehouses. There, they weigh the coltan, test the tantalum concentration with handheld analyzers, pay cash. Then they ship it out by plane or truck through neighboring countries. Rwanda, Uganda, Burundi, to mask where it came from. Rwanda officially exports hundreds of tons of coltan every year, even though it has almost no deposits on its territory. It's obvious what's happening. It's a transit point for Congolese coltan. The international community knows, but stopping the flow is hard. Borders in the region are porous, corruption thrives, tracing the origin of a specific shipment is nearly impossible. The coltan gets shipped to China, where most of the processing facilities are concentrated. There, it's melted in electric arc furnaces at temperatures exceeding 3,600 degrees Fahrenheit. What comes out is slag containing tantalum and niobium oxides. This slag gets treated with hydrofluoric acid, producing fluorides, which are then reduced to metals through complex chemical processes. Tantalum is incredibly refractory. Its melting point is around 3,000 degrees Celsius, third highest after tungsten and rhenium among all elements. That makes processing energy intensive and complex. Extracted tantalum is converted into powder, which is then pressed, sintered, and turned into anode foils for capacitors just a few micrometers thick. A tantalum capacitor works simply. thin foil is coated with an even thinner film of tantalum oxide, which acts as the dielectric. Thanks to the microscopic thickness of this film and the massive surface area of the porous structure, you get enormous capacitance in a microscopic volume. This allows electronics to be compact. Without a tantalum capacitors, smartphones would be the size of bricks. Legal coltan mining exists. Australia, Brazil, Canada have deposits and extract coltan using industrial methods that comply with environmental and labor standards. But the cost is higher because you have to pay decent wages, maintain safety standards, and rehabilitate the land. Congolese coltan, extracted through what's essentially slave labor, is cheaper, so demand for it persists. There are also synthetic alternatives. Ceramic capacitors based on barium titanate can replace tantalum capacitors in some applications. They're cheaper and aren't linked to conflict. But for the most compact devices with high reliability requirements, tantalum remains irreplaceable. Military electronics, medical implants, aerospace equipment, they only use tantalum. Tantalum demand holds steady, around 2,000 tons a year. That doesn't sound like much compared to the millions of tons of copper or steel, but given its rarity and concentration in one region, even that amount creates enormous pressure. Every new smartphone, every data center, every 5G cell tower requires tantalum capacitors. Tantalum prices fluctuate between $150 and $300 per kilogram for the metal, or the equivalent for ore depending on concentration. For comparison, gold runs about $60,000 per kilogram. Tantalum's cheaper, but you need way more of it. And extraction is concentrated in a conflict zone, making it strategically critical. The environmental fallout is horrific too. The Congo jungle, one of the planet's largest tropical rainforests after the Amazon, is home to unique species. But artisanal mining is wrecking ecosystems. Forests get chopped down for mines and miner camps. Rivers become polluted with washed-out rock that kills fish and aquatic life. Poaching thrives. Miners hunt wild animals for food. There are attempts to recycle tantalum from electronic waste. Old cell phones, computers, devices contain tantalum capacitors. Technologies exist to extract and recycle them, but economically it's tough. You have to collect massive quantities of old devices, disassemble them, isolate tiny components, remelt everything. Right now, only 5 to 10% of tantalum comes from recycling. Some activists are calling for a boycott of electronics, or at least mindful consumption. Don't swap your smartphone every year. Repair instead of tossing it. Buy used. But here's the reality. Most people don't even know about coltan and the problems tied to it. Manufacturers don't advertise the dark side of their shiny gadgets. There's hope in technological progress. New types of capacitors are being developed that could eventually replace tantalum ones. Graphene supercapacitors promise even higher capacity in smaller sizes. But mass production is years, maybe decades, away. For now, tantalum remains a critical element of the digital age. The irony? Congo is one of the poorest countries in the world, despite its incredible wealth of natural resources. Cobalt, coltan, copper, gold, diamonds, all buried in Congo's soil. But corruption, conflict, and exploitation by foreign companies mean that wealth never reaches the people. It's a classic resource curse, when natural resources become not a blessing, but the cause of endless wars and suffering. Picture this. There's an industrial process where almost 80% of the material just vanishes, but what's left becomes exponentially more valuable. How can wood lose nearly all its mass and transform into a global energy resource that countries pay billions of dollars for? Every year, this product makes a journey from living forests to cargo that crosses oceans, fueling everything from backyard barbecues to high-tech industries. But behind the apparent simplicity lies a dangerous stage where one mistake can destroy dozens of tons in minutes. In this video, you'll see how fire is controlled without flames. And by the end, you'll learn a fact about charcoal that'll completely change how you think about its true cost. Every year, the world burns through roughly 73 million tons of charcoal. That's nearly 200,000 tons a day, enough to bury hundreds of stadiums under a thick blanket of carbon. Despite the rise of gas and electricity, the global charcoal market is worth $3 billion annually. It all starts at raw material yards, where millions of tons of freshly cut logs arrive every single day. First stop, automated sawing lines. The wood gets chopped into standardized lengths, then moves on to hydraulic splitters. Massive steel blades, under incredible pressure, crack the logs into smaller pieces with uniform cross-sections. This isn't for looks. If the logs are too big, the outer shell carbonizes completely while the core stays raw. If the pieces are too small, they'll burn up too fast, turning into brittle charcoal that crumbles into powder. Uniformity of size. That's the foundation of quality, laid down before the first spark ever appears. Freshly cut wood contains 40 to 60% moisture by weight. Evaporating that much water directly in the kilns would be wildly inefficient, so the wood heads into sealed drying chambers. Each batch processes roughly 28 tons of wood over 12 hours. Powerful fans and circulation systems push hot air evenly through the stacks, dropping moisture levels to the critical minimum needed for safe transition to the carbonization stage. After drying, the wood gets loaded into giant industrial kilns. One kiln can hold around 55 tons of wood. This is the most critical stage. The kiln entrance is sealed tight with brick and a thick layer of special clay mixed with sand. This creates a low oxygen environment where combustion doesn't happen. Instead, you get pyrolysis, the chemical breakdown of wood through heat. The process runs nonstop for 7 to 10 days. When the internal temperature hits 572 degrees Fahrenheit, thick white smoke starts pouring from the vents. That's the operator's signal that transformation has begun. Operators, or automated systems, precisely control the air supply. There needs to be just enough oxygen to sustain the reaction, but not enough to let the wood burst into open flame. The result of this process? 55 tons of wood becomes just 11 to 13 tons of finished charcoal. Almost 80% of the original mass is lost, but what remains is pure carbon, lighter, more energy dense, and a cleaner burning fuel. When pyrolysis is complete, the charcoal still holds extremely high internal temperatures. Even the slightest contact with oxygen at this stage can trigger spontaneous combustion. To prevent disaster, the charcoal is left to cool in sealed conditions for 10 to 14 days. It's a test of patience. One tiny crack in the seal, and dozens of tons of product turn to ash in minutes. After full cooling, the charcoal goes through mechanical sorting. Large intact chunks 5 inches long are considered premium product. Every year, just one large plant's automated packaging lines process about 22,000 metric tons of this charcoal, which then gets shipped all across Europe. But what about the small fragments and charcoal dust? At a modern facility, nothing goes to waste. All the charcoal scraps get ground into powder and mixed with natural binding agents, like cassava or cornstarch. The resulting mixture is compressed under high pressure into briquettes, cylinders, or perfectly uniform pillows. These briquettes go through final drying at 280 degrees for 2 hours, becoming dense and stable fuel. When you look at the logistics side of a large modern plant, the numbers get even more mind-blowing. In just one sector, premium lump charcoal production, a single automated packaging line can process over 44 million pounds of product annually. That's tens of thousands of tons of finished fuel, requiring an unbroken supply chain of sourcing, packaging, and transportation. This intensity of operation demands perfect synchronization of every stage, from timber harvesting and days-long carbonization to the instant bagging of finished product that ships worldwide. Charcoal, born from living wood and forged in the fire of sealed kilns, is the result of a remarkable marriage between natural abundance and human engineering. It's a process where wood sacrifices its physical mass and moisture to preserve what matters most in its remains: pure, stable energy, locked away in the form of carbon. Every single charcoal block becomes proof of how humans learned to tame the element of fire, transforming forest resources into a compact and incredibly efficient energy carrier that continues to drive global civilization forward, despite changing eras. When we look at the charcoal production map, it becomes clear that the world is sharply divided between giant producers and equally massive consumers. Today, the undisputed leader in global exports is Indonesia. Just imagine, this country supplies nearly 22% of the entire global charcoal market. Its annual revenue from selling this product exceeds $400 million US. As for those buying this resource, that's where things get even more interesting. China leads the world as the top importer, accounting for over 11% of global imports. This isn't just about culinary traditions. Charcoal is irreplaceable in high-tech manufacturing. Think pure silicon for semiconductors. Right behind China, Saudi Arabia, Japan, South Korea, and the US. In these countries, demand comes from two places: the restaurant industry and backyard culture, which pumps billions into the economy every year. The total value of global imports in 2024 alone, nearly $2 billion. Technology keeps pushing forward, especially when it comes to efficiency. Modern plants using pyrolysis retorts, those same ovens we talked about, can squeeze every last bit out of the wood. Traditional earth pits. They give you 15 to 20% charcoal from the wood you load in. That's it. But modern systems, they're pushing 30, even 40% yields. That's massive for the environment. Same amount of fuel, millions of acres of forest saved. And here's the thing, agricultural waste is the new game. Coconut shells, corn cobs, making charcoal without cutting down a single tree. These numbers prove something crucial. Charcoal isn't some relic of the past. It's a dynamic market adapting to modern demands. We're talking billion-dollar operations, cutting-edge material science, and a lifeline for billions of people worldwide. Every ton of charcoal crossing the oceans, it's a piece of a massive energy puzzle. And production efficiency isn't just a nice-to-have anymore. It's the key to keeping our planet in balance. Every year, deep within the planet, a process unfolds without which the modern world would simply fall apart. A metal almost no one talks about determines the fate of reactors, skyscrapers, and engines operating at the edge of possibility. It's extracted where the air is thin, in quarries deeper than skyscrapers, and most of this substance never reaches human hands in pure form. Why do nations compete for deposits where this metal's content is merely fractions of a percent? How does a gray rock give birth to an alloy that withstands hellish temperatures? And most importantly, why wouldn't super strong steel exist without it? Stay until the end, and you'll discover the hidden role of molybdenum that even textbooks don't tell you about. The world's largest molybdenum reserves are concentrated in complex deposits where molybdenum is closely associated with copper, forming joint mineral formations. These deposits form under special geological conditions, and the world's leading countries control their extraction, ensuring the global supply of this strategic metal. Chile holds first place in global molybdenum production thanks to the giant Chuquicamata deposit, considered one of the largest on the planet. Located in the Atacama Desert, at an elevation of over 9,000 feet above sea level, this deposit is a true legend of mining. Here, molybdenum is extracted as a byproduct during copper ore mining. From each ton of copper ore, about 45 pounds of molybdenum concentrate is produced. Annual output exceeds 30,000 tons of pure molybdenum, making Chile the supplier of 30% of the global market. Operations are conducted in an open-pit mine 1,200 feet in diameter and half a mile deep, where giant excavators and conveyor systems are used to transport the ore. In the United States, the key site is the legendary Climax deposit in Colorado, which provides about 20% of global molybdenum production. This unique geological wonder of the San Juan Mountains contains billions of tons of ore with molybdenum concentrations up to 0.3%. Extraction here began back in the 1920s, and today the Climax pit is one of the largest in the world. Its area reaches 2,500 acres, and its depth is nearly 2,000 feet. Freeport-McMoRan is investing billions in modernization, using automated systems and green technologies to cut emissions. From here comes high-grade concentrate that's exported to Europe and Asia. China and Peru are also aggressively developing their deposits. In China, the leading sites are in Henan and Shanxi provinces, where they mine over 80,000 tons annually. And in Peru, the massive new Racio de Alto deposit promises to become one of the largest. Here, molybdenum is extracted alongside copper at depths reaching 6,500 feet using underground mines. The project, run by Southern Copper, involves $2 billion in investment and projected output of 20,000 tons of molybdenum per year starting in 2025. The uniqueness of these deposits comes down to geological processes. Molybdenum crystallizes in porphyry copper ores under the influence of magmatic hotspots, zones where molten magma penetrates the Earth's crust, enriching the rock with metals. Ore is extracted through open-pit mining at surface deposits or underground methods in deep mines, where drill rigs and blasting operations are used. After crushing, the rock is enriched through flotation, a chemical process where molybdenum minerals are separated from waste rock, yielding a concentrate with a metal content of 45 to 50%. This stage is critically important because it determines the efficiency of subsequent processing. These deposits don't just supply raw materials for metallurgy, they drive the development of extraction technologies in extreme conditions, from desert quarries to high-altitude mines. The molybdenum from them becomes the foundation for ultra-strong alloys that are transforming industry. The production process for ferromolybdenum starts with molybdenum ore arriving at the plant as large chunks of rock from the deposit. First, the ore gets loaded into powerful crushers, giant mechanisms that look like massive jaws, breaking the rock down into fist-sized fragments. Rumbling and dust fill the air as hammer or cone crushers convert tons of ore into fine particles. Next, the crushed ore feeds into mills, cylindrical drums about 10 yards long, filled with steel balls. They spin, grinding the rock into powder. From here, the mass flows to processing plants where flotation happens. Foam is added to large vats of water and reagents. Molybdenite sticks to the bubbles and floats to the surface like froth, which is scraped off. The rest settles as waste. The resulting concentrate, a moist gray powder, is dried in rotary kilns at temperatures near 600 degrees Fahrenheit, transforming it into a finished product for smelting. This stage takes hours, but determines the quality of the entire chain. After roasting, the molybdenum concentrate transforms into pure molybdenum trioxide, a yellow powder ready for final transformation into ferromolybdenum. This stage is the heart of production, where electric arc or aluminothermic furnaces transform iron and molybdenum oxide into a charge that's then carefully refined. The process demands extreme temperatures, precise control, and heavy-duty equipment, because molybdenum melts at a whopping 8,587 degrees. Electric arc melting is the go-to method in modern plants. Massive electric furnaces, with capacities from 10 to 50 tons, are loaded with the charge. Graphite electrodes 40 inches in diameter create an arc with 300 to 500 watts of voltage, heating the mass to nearly 11,000 degrees. In this scorching plasma, the oxide breaks down. Aluminum surrenders its oxygen to slag, while the iron molybdenum melts into an alloy. The reaction is violent. Sparks, flames, the furnace roaring. Slag floats to the surface and gets tapped off by crane. Melting happens in vacuum or argon chambers to prevent oxidation. Aluminothermic smelting, an older but effective method for small batches. In reaction crucibles, they mix molybdenum with aluminum powder and iron, then ignite it with a magnesium ribbon. The exothermic reaction instantly heats the mixture to the required temperature, reducing the metal in 5 or 10 minutes. Slag is removed mechanically. This method is cheaper but less pure. The resulting charge is refined, purged with argon to remove gases. Flux is added to clean out impurities. Spectrograph analysis monitors composition every 15 minutes. Refining takes 1 to 2 hours, bringing purity up to 99.5%. The finished ferromolybdenum, a silvery melt, is poured into molds for briquettes weighing 2 to 110 pounds. On the conveyor lines, the molten metal pours into steel or cast iron molds, cools under water spray for about 20 minutes. The briquettes get crushed by vibrating hammers, sorted with magnets, and packed into 2-ton barrels. The surface is shiny, pore-free, ready to ship. Ferromolybdenum in those 2-ton briquettes. It's the secret ingredient for steelmakers, because without it, you can't make ultra-strong steel that'll survive the hell of industry. It gets shipped to electric steelmaking plants all over the world: China, the US, Europe, Turkey, India. There they crack open the briquettes, load them into converters or electric furnaces, along with iron and coal. Molybdenum makes the steel uniform, heat-resistant, corrosion-resistant, prevents overheating. At the steel mill, ferromolybdenum briquettes arrive in hoppers or containers and head straight to the breaking station. Workers in protective gear use hydraulic hammers or vibrating breakers to crush them into 2 or 4-inch chunks. The sharp crack of metal echoes through the shop floor, dust settling under the ventilation system. The broken fragments get weighed and sent via conveyor belt to the scales. Next comes loading into converters or electric arc furnaces. The converter, a giant 200-ton vessel, gets filled first with molten pig iron from the blast furnace. Then cranes dump in scrap iron, coal powder for carburization, and batches of ferromolybdenum. The molybdenum dissolves instantly, forming molybdenum carbides that stabilize the structure. In an electric furnace, the process is similar but more precise. An arc from graphite electrodes melts the charge. Ferromolybdenum is added in portions through a hatch. Oxygen is blown through for refining. Gases are vented. Molybdenum makes steel uniform, heat-resistant, corrosion-resistant, and resistant to overheating. No cracks under pressure. The molten metal is poured into a crystallizer, where finished steel comes out. The shop roars, sparks fly. Real industrial action. Every year, steel giants weighing hundreds of tons are born across the world. Chunks of metal heavier than 40 elephants combined. But here's the question. How do you transform a 400,000-pound red-hot block into a perfectly precise component for a nuclear reactor or aircraft turbine, where even a millimeter of error means catastrophe? Only a handful of facilities and machines on Earth can pull this off. Presses generating tens of thousands of tons of force, buried stories underground. Why a seamless steel shell matters more than any armor, how nations compete for control over these technologies, and what critical weakness of modern civilization heavy forging conceals. You'll discover by the end of this video. If you watch till the end, one fact will change how you think about the strength of metal forever. A chunk of steel weighing over 200 tons. That's like 40 elephants stacked together. Now imagine you need to transform this giant metal block into a high-precision component for a nuclear reactor or aircraft turbine. Sounds impossible? This is exactly what happens every day at the world's largest forging plants, where force, engineering, and precision create genuine metalworking miracles. Among the industry's most remarkable facilities, Japan Steelworks in the city of Muroran on Hokkaido Island holds a special place. Founded in 1907 with participation from British companies Vickers and Armstrong Whitworth, this plant today controls around 80% of the global market for large forged components for nuclear power plants. Here are hydraulic forging presses ranging from 3,000 to 14,000 tons of force, with the largest capable of working steel ingots weighing up to 600 tons. What makes this plant unique? First and foremost, the ability to manufacture nuclear reactor vessels as single, seamless structures. This is critical for safety. Welded joints are weak points where radiation can leak. JSW remains one of the few manufacturers in the world capable of creating such components without any welding. Modern giant presses are engineering masterpieces in their own right. Take, for example, the Schultz steel press in California, which delivers 40,000 tons of force. This machine weighs over 2,650 tons, stands 60 feet tall, and is sunk 8 stories into the ground. To support it, you need a concrete foundation almost 2 inches thick, reinforced with rebar up to 4 inches in diameter. The press is controlled by 12 electric motors, each pumping out 1,200 horsepower, and 24 main hydraulic pumps. When those pumps kick in, the machine can stop 1,700 tons of moving parts to within 1/10 of an inch, all without hydraulic shock that could damage the structure or the workpiece. The precision of this giant is staggering. It can control position to within limits and pressure to within 300 tons of the target value. It's like trying to stop a train 1 centimeter from the mark, over and over, with absolute reliability. The process of creating a massive forged component starts long before the metal ever sees a press. First, a huge steel ingot gets cast. Modern third-generation nuclear reactors need ingots weighing 500 to 600 tons. That's a colossal engineering challenge, making, heating, and moving this little grain of steel that has to stay hot during transport from the steel mill to the forging shop. The steel for these gigantic components has to be flawless. Japan Steelworks uses cutting-edge purification technology, argon blowing to remove impurities, and precise additions of manganese, chromium, and nickel to hit the exact hardness and strength targets. Every single step of the process gets monitored with maximum attention to detail. Once the heated ingot hits the press, the most spectacular part of the process begins. Giant hydraulic pistons, each the size of a small room, slowly descend with incredible force. The metal, glowing red hot, starts to deform plastically, taking on the desired shape. This isn't a quick strike, like old-fashioned hammers. It's controlled, massive pressure that lasts seconds or even minutes. During the forging of a 200-ton workpiece, it needs to be rotated periodically to ensure even processing from all sides. Special manipulators handle this, enormous mechanical arms that can carefully rotate the white-hot metal giant. These manipulators themselves weigh dozens of tons and are controlled by advanced coordinate systems, ensuring millimeter precision even when working with such colossal masses. Between passes under the press, the workpiece can be returned to the furnace to maintain the required temperature. Forging a large part can take hours or even days, depending on the complexity and size of the final product. The result of this titanic effort? Components our lives literally depend on. Nuclear power plant reactor vessels weighing over 500 tons, capable of safely containing nuclear reactions for decades. Steam turbine rotors weighing over 200 tons, spinning at tremendous speeds, generating electricity for millions of homes. Components for aircraft engines that withstand extreme temperatures and stresses. For the maritime industry, they manufacture crankshafts for ship engines and steering system components weighing up to 300 tons. These parts are used on the world's largest container ships and tankers, ensuring reliability during years of voyages at sea. You'd think forging is just applying force to metal, but it's actually a much more complex science. When metal deforms under immense pressure, its crystalline structure changes. The steel grains align along the load lines, creating a fibrous structure similar to wood. This directionality makes forged metal far stronger in the direction of the fibers than cast steel. Temperature plays a critical role too. Steel that's too hot can become too soft and lose strength. Too cold, it cracks under the press. Engineers must know exactly what temperature to work with each alloy to achieve optimal properties. After forging, parts go through heat treatment, controlled heating and cooling to hit the right hardness and flexibility. Then comes rigorous inspection, ultrasonic scanning to catch internal defects, X-rays, mechanical testing. Not a single hairline crack or void can slip through unnoticed. While Japan's Japan Steelworks dominated this field for years, competition's ramped up lately. China poured massive investment into heavy forging capacity. The biggest Chinese presses hit 80,000 tons of force. These are the most powerful machines on Earth, letting the country be self-sufficient in manufacturing components for nuclear power and aerospace. France's Framatome and 2 more Chinese companies round out the short list of manufacturers capable of creating the largest single-piece components for nuclear reactors. This is a global game where heavy machinery capabilities directly impact a nation's energy and defense independence. The history of heavy forging goes back to World War II, when Japan Steelworks manufactured the barrels for the largest guns on the battleship Yamato. Tragically, during an Allied air raid in July 1945, 200 workers at the main plant in Muroran were killed. But the company was reborn and transformed into a peaceful metalworking giant. Today, these technologies continue to evolve. Back in the 1950s, some experts predicted that aircraft manufacturing might need presses capable of 200,000 and 250,000 tons. Such machines still haven't been built. Even the Chinese giants are half that size. But progress doesn't stand still. Tesla has proven that manufacturing massive one-piece components can revolutionize production. The next generation of presses might actually reach that kind of incredible power. Sadly, not every country held on to its heavy forging capacity. The United States, once home to the world's most powerful presses, lost the ability to make the largest ingots. America's biggest steelmakers, like Bethlehem Steel, could only produce ingots up to 380 tons. Not enough for modern needs. That means the US depends on imports for critical components in nuclear power plants and heavy industry. Britain ran into problems too. Sheffield Forgemasters, the company that made components for the Royal Navy's submarines, planned to install a new 15,000-ton press back in 2010. The government initially allocated £80 million, but later cancelled the funding. This limited the country's ability to manufacture the largest nuclear power components on its own. Behind all this colossal machinery are people, engineers, metallurgists, press operators. Their experience and skill are invaluable. A forging master at these giant plants makes adjustments based on decades of experience. He knows how each alloy behaves, how long to keep it under the press, when to rotate the workpiece. What if I told you that inside the most dangerous machines on the planet hides a steel secret that can only be created once, and a mistake costs an entire nation? That there's an ingot that cools underground for 6 weeks and withstands pressure that would shatter mountains? This giant is born in fire, exceeding 5,000 degrees Fahrenheit, endures months of forging, blows of tens of thousands of tons, and thermal shocks that would explode ordinary metal into fragments. Stick around till the end. You'll discover what these monoliths are actually built for, and why, without them, the modern world would simply grind to a halt. It all starts in the foundry. To create a monolithic ingot, you need liquid steel of impeccable quality, poured into a mold in one continuous stream. This is a stage that demands maximum coordination, because we're talking about thousands of degrees and hundreds of tons of metal. A striking example of such an engineering feat was a record-breaking pour carried out by the British firm Sheffield Forgemasters in 2015. The company's metallurgists successfully handled the pouring of 607 tons of liquid steel into a giant casting pit. To put that volume in perspective, it's nearly the weight of a full-sized Airbus A380 passenger jet. The pouring process is critically important. The steel must not only be melted, but also purified to a level that meets the strictest customer requirements. For example, for reactor components. This means minimizing impurities, gases, and slag. A continuous pour ensures that there won't be any layered defects or boundaries in the ingot structure that would reduce its mechanical strength. During casting, the steel must be fully degassed. Oxygen and nitrogen levels are controlled at levels often not exceeding 20 parts per million. Excess gases can cause microvoids to form inside the monolith during cooling. Immediately after pouring the molten metal, which can exceed 2700 degrees Fahrenheit, time becomes the most critical factor in this process. Unlike small ingots that can cool quickly, a steel giant weighing hundreds of tons cannot be cooled rapidly. If cooling happens too fast, it leads to massive internal stresses, cracks, and structural defects because the outer layer solidifies while the steel inside is still liquid. To ensure uniformity of the crystalline structure, the 607-ton ingot was left to cool in the casting pit for 6 weeks. This is a controlled, incredibly slow process, during which the steel gradually solidifies, dropping to a temperature of around 2000 degrees. This slow crystallization allows the metal to avoid unwanted phase transformations and guarantees a high-quality macrostructure, which is the key to the strength of the future component. Only after this lengthy solidification period is complete, the steel monolith, which after shrinkage and removal of the defective top portion weighs approximately 320 tons, is carefully extracted from the ground. The extracted ingot, despite its weight, is not yet a finished blank. It has a cast, coarse structure with large crystals. To transform it into strong, homogeneous metal capable of withstanding extreme loads, forging is required. Forging 500-ton ingots demands hydraulic presses with working forces ranging from 10,000 to 20,000 tons. For example, forging the largest reactor components requires presses with a capacity of 40,000 tons. Before forging, the ingot is again carefully heated in specialized furnaces. This process can take weeks to guarantee uniform heating throughout the entire volume of metal. The forging itself is done on giant hydraulic presses capable of creating pressure in the tens of thousands of tons. The press breaks down large, brittle cast crystals. The pressure compresses the metal, eliminating microscopic voids that may have formed during casting. The metal gains a directional fibrous structure, which significantly increases its strength, toughness, and fatigue resistance. The forging process for such an ingot takes several months. It's a constant cycle of heating, pressing, rotating, and reheating. Each press stroke is a precise calculation aimed at achieving the required internal geometry and mechanical properties. The energy needed to maintain the furnace for heat treating ingots during a 2-week cycle can exceed 100,000 kilowatt hours. That's comparable to the annual electricity consumption of dozens of typical households. During heat treatment, the allowable temperature deviation in the furnace throughout the entire volume can be only 40 degrees, which requires the use of high-precision multi-zone control systems. After shaping the ingot, we move to heat treatment. This is the final, critically important stage for tuning the internal structure of the steel. A multi-ton steel monolith that's just survived months of casting and forging is like a clumsy giant whose final character hasn't formed yet. It's strong, but its internal structure is still chaotic, riddled with invisible internal stresses. The first step is normalization, or, as we call it, homogenization. The idea is simple. We basically stir the metal structure so it becomes absolutely uniform throughout the entire volume. This ensures that at every point in the workpiece, both on the surface and deep inside, the steel has identical properties. It's like evening out the temperature in an oven so your cake bakes perfectly. Then comes the most dramatic moment, quenching. The workpiece is heated to a very high temperature, bringing it to peak plasticity. And then, rapidly, but under strict control, it's cooled. This could be a water or oil bath. This shock to nature transforms the soft steel structure into something maximally hard and strong. This gives the part its core fighting strength, but there's one side effect. The metal becomes brittle as glass, and massive internal stresses appear. If you leave it in this state, it can crack from the slightest impact. That's why the final, and most humane stage is tempering. The piece is carefully reheated, but this time to a much lower temperature. The goal isn't to change the strength, but to release the internal stresses that formed during rapid quenching. This process is like taking a deep breath after stress. It increases the steel's toughness, making it resistant to impacts and loads, eliminating brittleness. Only after successfully completing this full month-and-a-half cycle of character hardening is the steel ready to become part of a reactor or a giant press. But what are these steel giants for, into which so much time and resources have been invested? They become critically important components in industries where the price of failure is unacceptably high. For example, in nuclear power, these ingots are transformed into key components of high-pressure reactors. Picture this: pressure, temperature, and radiation demand absolute reliability. And there can't be any seams or welds that might give way. You need just one thing: a solid, continuous monolith capable of withstanding extreme loads for decades. In heavy machinery, these giants become frames for the world's largest presses. These presses shape automotive frames, aircraft parts, and ship components. A frame that won't deform under thousands of tons of load has to be cast in one piece. And of course, there's power generation. Rotors for the largest steam turbines, or crankshafts for massive marine engines that drive supertankers and container ships. In these components, you need guaranteed strength against bending and secondary loads, and only steel produced through this incredibly complex process can deliver that.